Hello, I will present my work, which title is a flexible extension of the Weibull model for realistic failure rate patterns. It is a joint work with Professor Patrícia Antunes and Professor Dario Ferreira. In probability distribution theory, different methods could be put into use to expand the current standard distribution. The flexibility of a distribution can be increased through generalization. So many general distribution classes have been derived in recent years. Mudokar and Srivastava in 1993 added a parameter to the two-parameter Weibull distribution. The Weibull family is widely used in the reliability modeling due to its adaptability, and recent studies have also explored Bayesian approaches and machine learning tactics to estimate Weibull parameters more robustly. Recently, additional generalizations of Weibull-based distribution have been proposed. For instance, Dipty et al. In 2023 introduced the Burr-Third Weibull quantile function, demonstrating its applicability in reliability analysis. Their model combines the quantile functions of the Burr-Third and Weibull distributions, providing an alternative framework for analyzing lifetime data. Vidovi et al. In 2024 explored Bayesian inference methods applied to the Weibull model, ensuring proper posterior distributions and finite posterior moments under specific conditions. Mudokar in 1995, Cordeiro and Castro in 2011, and Eugene in 2002 developed an extension of the Weibull family. They define a new family of Kumarasvani-Weibull generalized distribution that we will name from now on from KWG to extend several widely known distributions such as the Weibull distribution. In that paper, it was presented the exponentiated Weibull family. This new class of distributions considers that for a baseline cumulative distribution function of this distribution is defined by equation 1, where A and B are bigger than 0, are two additional parameters whose role is to introduce skewness and to vary tail weights and demonstrated its flexibility to fit failure data. Thus, substituting Gx, the cumulative distribution function of the KWG, is obtained as equation 2, where lambda is a scale parameter and c is a shape parameter. The exponentiated generalized class extends several common distributions studied recently, such as exponentiated exponential, gamma, Campbell, Rechet, and Weibull distributions. And if we set alpha equal to 1, we obtain the exponentiated type distributions defined by Gupta et al. In 1998. The PDF of the KWG distribution is obtained by equation 3, or alternatively, the PDF can also be rewritten as equation 4, considering Gx equal to 1 minus this exponential. For example, the KW Weibull distribution developed by Cordeiro 2010 and Cordeiro 2011 is a special KWG distribution obtained by taking Gx in previous equation to be the cumulative distribution function of the Weibull distribution. The KW distribution is a special case of the KWG distribution with Gx in the uniform distribution on 0, 1, whereas the GX distribution corresponds to A equal to B equal to 1. Now, in this talk, the exponentiated Weibull exponential distribution, EWE, is presented, which is an extension of the Weibull distribution. The EWE distribution exhibits important hazard function shapes that are not possible with many traditional distributions. This distribution exhibits hazard function shapes such as increasing, decreasing, and upside-down bathtub, which are often observed in survival and reliability data, but are not captured by many classical models. Our proposed distribution, exponentiated Weibull exponential distribution, EWE, is expressed as this equation 5, where alpha, beta, and gamma are bigger than 0, and beta is a scale parameter, while gamma and alpha shape the distribution and its hazard function. There are other parameterizations of the probability distribution function of our proposed distribution, but our case aligns with the parameterization studied by Abbas in 2023, as this probability distribution function captures a wide range of hazard shapes, and our selection was guided by both theoretical and practical considerations, ensuring suitability for the problem addressed in our study. There is here in figure 1 a plot of our proposed distribution PDF for different parameter values. Let's move now and study the hazard function of our proposed distribution. As you know, the hazard function, or failure rate, represents the instantaneous rate of failure at time t, given survival up to time t. Intuitively, the hazard function tells us how likely the event is to occur in the next instant, assuming it hasn't occurred yet. So, the PDF to the survival function ST is, and our hazard function is given in equation 6, where ST is the survival function. Different shapes of the hazard function correspond to different types of failure behavior. An increasing hazard implies that the longer a component has been in use, the greater the chance it will fail in the near future. A decreasing hazard implies that the component is more likely to fail earlier, and those that survive longer are increasingly reliable. And constant hazard indicates a memoryless process, meaning the probability of failure in the next moment is independent of how long the system has already survived. This behavior is characteristic of the exponential distribution, which is commonly used to model random and unpredictable failures. For our distribution, the hazard function is given by equation 7, and the hazard function is quite flexible and can exhibit various shapes, including increasing, decreasing, bathtub-shaped, and unimodal, depending on the values of the parameters. Rather, it's the interaction between alpha and gamma that governs shape. Beta controls scale, but does not by itself define the shape. This flexibility of hazard function of our proposed distribution makes our distribution suitable for modeling a wide range of lifetime data in reliability and survival analysis. In figure 2, we can see the plots of the EWE hazard function for certain values of the parameters, illustrating the diverse failure rate behaviors for different parameter values. Now let's study the MGF. And to compute the raw moments of the EWE distribution, we expand the following term in the probability distribution function using the binomial series presented in equation 8. Substituting this expansion into the definition of the R's raw moment, we obtain equation 9. So the moment generating function can be written as a power series as we have here in equation 10. By interchanging the summation order, the moment generation function can be written in a compact form, like in equation 11, and this form can be used to approximations or numerical evaluation of the moment generation function. Let's move to maximum likelihood estimation. Let's consider x1, x2, xn, a random sample from the EWE distribution. The log likelihood function L with these parameters is given by equation 12. To obtain the maximum likelihood estimates of the parameters, we find the first derivatives of the natural logarithm of the likelihood function given in equation 12 with respect to alpha, beta, and gamma, and equating them to 0, getting the following equations. The equations 13, 14, and 15, where we have the derivatives with respect to different parameters. The MLEs of the unknown parameters can be obtained by solving the system of equations given in these equations. A common numerical technique to solve these equations is the Newton-Raphson method. The efficiency of the method depends on the number of interactions required for convergence, as well as the computational cost per interaction. Since our model involves only 3 parameters, this results in an insignificant computational burden, ensuring feasibility even for large datasets. Now, we will present a simulation study that has been performed using R software to illustrate behavior of the MLEs in terms of the sample size and to assess the consistency of the estimators for parameters of our proposed distribution. We will present the biases, mean square errors, and variance calculating by generating different random sample sizes. Sample sizes used in the simulation study to estimate parameters are n equal to 20, 30, 50, and 100, and experiment was conducted 1,000 times. The outcomes of the simulation are summarized here, and after varied values of the parameters across all simulations, we observe that as the sample size increases, the mean, bias, MSE, and variance tend to decrease. Now, let's move to the section that presents a real-life dataset description. We will use a real-life dataset study by Weibull in 2011 that represents the survival times in months for breast cancer patients. We compare how well the proposed EWE model fits the data with how well the other models fit, namely, we compared our proposed distribution with exponential, exponentiated exponential, Weibull, and Weibull exponential using model selection criteria. To evaluate the competitive models, we consider several goodness of fit statistics such as AIC, BIC, KS statistic, and we have the table 1. And in this table, we present the different distributions, and following Abdullahi in 2021, where smaller values indicate better model fit, the results in this table shows that our proposed distribution achieves the lowest AIC and BIC scores among all the fitted models. Here in this figure 3, we'll also present a time to failure plot. And is plot is also known as a survival plot or reliability plot. That is a graphical representation used to visualize the time to failure. The curve shows a rapid initial decline in survival probability, indicating a high failure rate early in the observation period. The steepest drop occurs within the first 23rd time units, suggesting that is a critical period where failures are most likely to occur. For example, at time 0, there were 121 subjects still under observation or at risk, and for example, at time 50, only 43 subjects were still under observation, as we can see here. Now, in our approach, we also made a comparison between the estimated probability distribution function of these 5 distributions and our distributions of the breast cancer dataset. Next figure, the figure number 4, shows the estimated probability density function for different distributions fitted to the dataset. Here we have the estimated PDFs of the cancer dataset for the 5 distributions. And in figure number 5, we have estimated cumulative distribution functions of the cancer dataset for 5 different distributions. So, in the first plot, the EWE in green line stays nearer to the black empirical CDF line, indicating that its predicted probabilities are closer to the observed data at all points. You can see there the green line. Competing distributions, red, blue, yellow, and purple, deviate more from the empirical CDF, especially at lower and higher data values. A better CDF fit means the model more accurately represents the probability structure of the observed data. In conclusion, our proposed distribution has demonstrated superior performance in modeling various real-world phenomena compared to its submodels and related distribution. And an application to one real-life data shows that our EWE proposed distribution is a strong competitor and can also be used as an alternative model in modeling lifetime processes. And I want to thank your attention. There is some references